Welcome to the third video in Unit 4, where we're discussing the reactivity and structure of carbonyl compounds. So we'll continue with the series of analyses looking at what happens as we change the substituent of a carbonyl and how that influences electrophilicity of the carbonyl carbon. So what we're changing here is whether we have a methyl group or some kind of an alkyl substituent like we'd expect in a ketone. So this is an example of a ketone. We actually saw this exact molecule in video 2 when we compared it to an ester and an amide. But we're going to compare this ketone to an aldehyde now. So we're basically changing our methyl into a hydrogen. And we can see from the measured half-lives of these reactions involving water, so the same reference reaction we saw in video 2, the aldehydes are quite a bit more electrophilic. At least more electrophilic than the ketone. It's a fairly significant difference. It's not as dramatic as we saw with the ketone versus an ester or especially an amide in the previous video, but there's clearly something that's going on here, and it must be related to the differences between a hydrogen and a methyl group. So last time we talked, we established that we always want to analyze substituents for both inductive and resonance effects, and we'll do that here as well. We'll start with the ketone since we've actually done that analysis already in the second video, so this is kind of a reminder. If we're looking at induction, we're trying to establish if there's any kind of bond dipole between the carbonyl carbon and the substituent atom that's actually attaching the substituent to the carbonyl. So that would be a carbon-carbon bond in this particular case. That bond is going to be nonpolar, like completely nonpolar, or based on other kind of groups that are remote to this specific bond, only weakly polarized. So we could say there's no inductive effect. And like we established in the previous video, the carbon here is not able to participate in any kind of resonance relationship to the carbonyl carbon because this carbon has no p orbitals, it has no lone pairs, it has no pi bonds. So there's no resonance effect. And that's also going to be true for our hydrogen. Our carbon-hydrogen bond is only going to be very weakly polarized and actually toward the carbon. So if anything, the hydrogen is like a very weak inductive donor, but that effect is so small, I'm just going to say that there's no inductive effect. It should be negligible. One of the reasons I know that I can justify this assumption is that if this inductive effect were not negligible, for instance, if this hydrogen was actually a pretty good donor of electron density in induction, we should actually expect to see the aldehyde carbonyl be less electrophilic than the ketone, where there really truly is no inductive effect. That donation should make the carbonyl carbon less partially positive and therefore less electrophilic. The data doesn't support that, so I feel pretty confident in this kind of assumption. I also know that this hydrogen is definitely not going to have any resonance effect with the carbonyl. There's no electrons that can donate from the hydrogen into like a pi bond here. We know that hydrogen doesn't even form two bonds. After having done our analysis for the hydrogen substituent and our methyl substituent, it looks like they're doing very similar things to the carbonyl carbon. And in essence, neither of them are doing much at all. But that's confusing because the experimental data, the half-life data, suggests that the aldehyde is actually quite a bit more electrophilic than the ketone. There must be other features of these substituents, the only place the structures are changing, that we haven't yet talked about. Those will correlate with what we see in the experiment. So let's talk about some new variables. One of them isn't so new, it's just that we haven't discussed it yet, and that's sterics. This came up in the second video. If we think about a hydrogen, it's going to be a lot smaller than a methyl. Or if our ketone were like something else besides a methyl group, same concept would apply. An aldehyde is always a hydrogen, but a ketone, methyl is as small as you're going to get, realistically. So we could say a methyl or an alkyl group. So the aldehyde carbonyl carbon is less hindered than the ketone carbonyl carbon. as we established earlier, all else being equal, well, that's what this stuff in blue is telling me, at least so far, the carbon should be more electrophilic if it's less hindered. And I'm going to abbreviate electrophilic E+ here. Just since the word electrophilic is long, we're going to be using it a lot. I'm going to be writing it on the board. And as we go later in the semester, I'll start to use this notation when we start to use the concept of electrophilicity to make predictions about where reactions will happen in structures. Right? So just a reminder that E+ is electrophilic. All right, so sterics is one option that does fit the data, right? The aldehyde carbonyl carbon, less hindered and more electrophilic, therefore the half-life should be smaller. Check. The other factor that we haven't talked about yet is a little bit less obvious, and it comes from a concept that you probably have encountered before where we deal with the number of substituent atoms, or groups rather, that are attached to something that's positively charged. So if you think back to learning about carbocation stability, when you talked about SN1 reactions, you probably heard something like tertiary carbocations are more stable than secondary carbocations. And you probably heard something like the alkyl groups that make up those substituents, like there would be 3 of them in a tertiary carbocation, but those are somehow donating electron density. That's what would be required to stabilize a carbocation. That's a positive charge, so moving electrons toward that point should be stabilizing. Well, we know that our ketone we could represent in its minor resonance structure as a carbocation. We talked about that in the first video of this unit. So I'm going to draw that here. And we can see now that we have these 2 alkyl substituents that are right next to our carbocation. So we basically have the same concept that you saw in SN1 chemistry. Both of these groups can donate electron density. Whereas if I do the same thing with the aldehyde, give myself some space to draw the resonance structure. Like so. Oops, positive charge. Oh well. I've only got one donor group, just the one methyl that's a constant, right? So we've got more donors in the ketone than we do in the aldehyde. If I've got more donors here, there's less positive charge buildup on this carbonyl carbon, and that means our half-life should go up or become longer, and that's what we see. So this concept of alkyl groups acting as donors of electron density isn't induction. That wouldn't make any sense, right? This carbon-carbon bond isn't really polar, not in the same way we think about like a carbon-oxygen bond or a carbon-fluorine bond. Instead, this concept has a different name. It's sometimes called hyperconjugation. It shows up anytime we have an alkyl substituent adjacent to a p orbital. So it could be a case like with the carbocation, we know that there's an empty p orbital on the carbon here. In an alkene, for instance, there's p orbitals that make up the pi bond. And if we wanted to look at the major resonance structure of a carbonyl, we know that we've got a carbon-oxygen pi bond, so this carbon has a p orbital to make the pi bond. The methyl group would be adjacent to that. So this concept of hyperconjugation, in essence, we can say this is when alkyl groups donate electron density to p orbital, to sp or sp2 hybridized atoms. Remember that these are the 2 hybridizations where the atom would have an atomic p orbital left over. So this could be like carbocations, could be alkenes, and in our case, it could be carbonyls. All right, so let's add this feature now onto our list where we're analyzing the stuff in the box. So our methyl group is not an inductive donor or acceptor, so there's no inductive effect. There's no resonance effect, but the alkyl group is a hyperconjugative donor. That methyl group is donating electron density to the carbon center. we would see that maybe a little bit more clearly if we were to analyze the minor resonance structures of the carbonyls. So on the other hand, this hydrogen is not an alkyl substituent. So there is no hyperconjugation effect, which I'm going to abbreviate as hyperconj. So now we can start to see where these differences arise. It's not induction, it's not resonance, it's partially hyperconjugation, where the methyl's a donor, and that's going to actually decrease the amount of positive charge on the carbonyl carbon and make it a weaker electrophile than an aldehyde, which has no hyperconjugation. And it's also a steric effect, right? This methyl group also takes up some space, and that's going to slow down how quickly the reaction can occur where a nucleophile is approaching our carbonyl carbon. So really the purpose of this section of the video is to introduce that steric effects can matter, but mostly it's to introduce this concept of hyperconjugation, which we can reliably predict will happen with an alkyl substituent. So in the next section of the video, we'll be diving a little bit more deeply into the nature of resonance donation in these kinds of carbonyl species, because it's not as simple as saying something is a donor or not. Let's compare an ester to a thioester. So these look very similar. All I'm doing is really changing oxygen for sulfur. So I'll put my analytical boxes in here. And we notice something kind of remarkable, and that's that the ester is far less electrophilic than the thioester is, which is a little bit surprising. If we look at the stuff in the box, we can do our analyses. So we know that the oxygen and the rest of this group here, the substituent, these are inductive acceptors. We know that sulfur is like slightly more electronegative than carbon, so the sulfur group would be like a very weak inductive acceptor. It's kind of shocking how similar sulfur and carbon are in terms of electronegativity, so this is a vanishingly small effect. So I'll say a weak inductive acceptor. Okay, so if that's all we had, then we would expect the ester to be more electrophilic than the thioester, right? We're moving more electron density by induction here than we would be here. The data contradicts that. So we know that there must be something else other than induction that's different between these two structures. We also know that this oxygen is a resonance donor. The way I know that is actually pretty simple. There's an oxygen attached to the carbonyl carbon, and that oxygen has a lone pair. That's all I need to know to establish there'll be this resonance donation, this lone pair adjacent to the carbonyl carbon. So I'm going to go ahead and draw the resonance structure. We've seen this before in the second video in our series, but we'll want to talk about this resonance structure, and that is for the corresponding thioester. So there's our resonance structure, minor resonance structure here. We could do the same thing here. Oh, well, the sulfur's got a lone pair, so that looks good. It looks to me like the sulfur is also a resonance donor. Okay, well, that's weird. So far, it looks like the only differences are with induction, which again, doesn't match the data. So I'll draw my resonance structure now. All right, very good. Maybe it's hyperconjugation. Well, this oxygen is not an alkyl substituent. The alkyl substituent needs to be actually attached to the carbonyl carbon for hyperconjugation to be relevant here in a meaningful way. So there's going to be no hyperconjugation. And that's true for the sulfur case also. We're going to say no hyperconjugation. Oh boy, we're kind of an impasse. We're going to have to think a little bit deeply here about resonance, I think, because that seems to be the only place where we have not yet talked about relative impacts, right? So we have like inductive acceptor versus weak inductive acceptor. Maybe we can talk about differences in resonance donation for an oxygen versus a sulfur. Based on the data, I already know that it has to be the case that this carbonyl carbon of the thioester is more positive than for the ester carbon. What that basically means is if it's going to be about resonance, then we would need to be able to say that the sulfur is a weak resonance donor. That means essentially that we're not going to be pushing much electron density toward the carbon. That makes it relatively electrophilic and the faster half-life than the ester case. Why would it be the case, though, that the sulfur is a weak resonance donor? Well, it comes into effect because of the nature of carbon-sulfur bonds. If we look at the periodic table, we see the carbon's on the second row and sulfur's on the third row. So that tells us that we've got a CS pi bond. That's what this resonance structure requires. In order to donate this electron density, I need to be able to access carbon-sulfur pi bond character. We know that carbon-sulfur pi bonds are extremely weak. Because the bond really barely forms at all. If we think about this bond, it's long. In part because sulfur is a very large atom. If I took a golf ball, that would be my carbon, and a softball, that would be my sulfur, and I put them next to each other, the distance between the centers of those two spheres is going to be a lot longer than if I took two golf balls, for instance, two carbons, or a carbon and an oxygen, and put them together. So this bond is very long, and that matters all the time. You learned back in Gen Chem that usually longer bonds are weaker bonds, but for a sigma bond or a single bond, it's not that consequential because the bond forms by orbitals touching like this. And really they overlap. So they kind of have a place where they're stacking right on top of each other. And as the bond gets longer, well, that stacking gets littler, and that makes the bond weaker. Basically, what I'm saying when the bond is weak is that I have to be able to break those apart. But a pi bond is different. A pi bond is a side-on interaction like this. So if I'm really close together, these things can lean in a little bit and I get some overlap. That's what a bond is. But if I separate them along the bonding axis here, now it's much harder for these p orbitals to interact, and that's going to make it much easier to destroy the interaction. Another way of saying that is separating those p orbitals that are interacting side-on makes the interaction very weak. And that's a consequence of the fact that sulfur is a third row element. So we have this larger atom, sulfur, third row, and that means that even though it has the lone pair to donate, it doesn't do a very good job of it because essentially the way in which it would try to donate, making this sulfur-carbon pi bond, is essentially, well, it's not impossible, but it doesn't work very well. And that makes sulfur like, well, I'd like to donate, but I kind of like can't. Whereas oxygen, second row element, we don't have this problem with like ultra long carbon oxygen pi bonds. These are normal looking. That means that they're relatively strong pi bonds. And so oxygen can be a very powerful resonance donor. Our takeaway here is that essentially large atoms, so like third row and especially things like fourth row elements, they really don't have powerful resonance effects generally. Resonance effects are weaker in larger atoms, which for our purposes we can treat as third row or below. So not only do we have to think about the strength of inductive effects, which is going to be based on the extent of a bond dipole, we also have to think about the extent of resonance effects. And in part, that's going to be dictated by whether or not it's really feasible to make the new pi bond that we would need for the donation to actually happen. What we see is that for third and fourth row elements, that's really not feasible in a meaningful way. And so those third or fourth row elements, even though they look like they could be donors, are not very good at it. And that's going to have consequences for reactivity. So like a thioester, for instance, is a lot more electrophilic than you might expect just based on the drawing, because embedded within the drawing is this concept that the sulfur is really not a good resonance donor, whereas an ester has a very powerful resonance donor in the oxygen. So in the next section of this video, we'll be continuing to explore how resonance effects can differ in strength now not based off of size, but based off of electronegativity differences. Here we'll circle back to our amide versus our ester. So we actually looked at this comparison in the second video of this unit, but I want to circle back because I want to talk about resonance effects and the relationship to the nature of the atom doing the donating. We saw that size of that atom can matter a lot, for instance, oxygen versus sulfur. And that kind of jives with how we talked about conjugate bases in a very general way, where we saw that in a column comparison, so like oxygen versus sulfur being in the same column, atomic radius tends to be a very important characteristic that we want to consider. But we could also think about what happens when we're comparing two atoms that are in the same row of the periodic table. So we've established previously that like electronegativity differences can be important there. And we'll see that in our example looking at an amide versus an ester. What we had decided earlier was that the NH2 group of the amide is a weaker inductive acceptor than the OMe group of the ester, which was based purely on the fact that nitrogen is less electronegative than oxygen, and therefore exerts less of a pull on the electrons between the carbon and the nitrogen than would be the case for the electrons in the bond from the carbon to the oxygen. I've drawn the resonance structures, or minor resonance structures, for these carbonyls where the substituents have been involved. One thing I notice is that a carbon-nitrogen pi bond, that's just fine, right? It's 2 second-order elements, so I don't have a size mismatch here. The same thing is true for carbon-oxygen, so any differences I might see in terms of resonance aren't going to be related to like a pi bond being too long, for instance. The other thing I notice in the data with the half-lives is that this is such a big difference in reactivity that I'm uncomfortable thinking that this is all about induction. Remember when we looked at pKa trends in the second unit of the class, we saw that induction does change acidities, but those changes were not huge, especially when we compared the differences in pKa's for those acids versus acids that were impacted by conjugation or resonance effects. So we want to also establish the fact that maybe this nitrogen is a stronger resonance donor. Whereas the oxygen is a weaker resonance donor. That would be consistent with this big difference in half-lives. So not only is it the case that I'm removing less electron density from the carbonyl with my nitrogen, I'm also dumping more back by resonance than I am with oxygen. So both of those differences combined, that could lead up to a big difference in reactivity. Well, why would it be that the nitrogen is a stronger resonance donor? Let's look at the minor resonance structures, and we notice that this atom is becoming positively charged. So when we think about resonance hybrids for these carbonyl structures, there's going to be some positive charge that actually builds up on the substituent atom, in this case nitrogen versus oxygen. Which of those two elements, nitrogen or oxygen, is better able to handle positive charge? Well, we know that electronegativity tells us something about the propensity of an atom to stabilize negative charge. It seems to me that positive charge would also be relevant here. If an element's really electronegative, it probably doesn't like positive charge, or at least as much as an element that's less electronegative. So we could say something like, nitrogen is less electronegative, En, than oxygen, and therefore a better donor. We're looking at it here in terms of the effect of having donated. That atom is becoming positively charged. We know nitrogen is probably a little bit more okay with that than oxygen was. We could also look at it from the perspective of the lone pair before the donation happens. If you're a lone pair on nitrogen, you're like, yeah, this is pretty good. It's like better than carbon. It's better than boron, but it's only okay. That's what the electronegativity of nitrogen means to the electron pair. Nitrogen's an okay spot. But if you're a lone pair on an oxygen, you're like, hey, I'm on the second most electronegative element in the universe. So like my lot's pretty awesome right now. If that's true, why would it want to be donated? Well, it probably doesn't exactly want to, and it probably, to some extent, will fight this preference to donate into the carbonyl. So both of those different perspectives, either what happened, where we're looking at positive charges, or, well, will the lone pair ever leave the place it is? And that's what would be required for donation. That's another way to look at it. But they give you the same result, that nitrogen is a better resonance donor than oxygen because of the difference in electronegativity between nitrogen and oxygen. So you could test this in a variety of ways. For instance, you could think about a compound where instead of having an NH2 group in the box, you could have a fluorine. That compound would be called an acid fluoride. And you probably could make some predictions about the reactivities of acid fluorides. So that's actually a good exercise for you to do to make sure that you've internalized this logic. You could think about, well, for the acid fluoride, should my half-life be less than 2 years, between these two numbers, or more than 4,000 years? And I'd be interested to hear what you think about that on the discussion board. So in the final section of this video, we'll be looking at a compound that's similar to an acid fluoride. We'll actually be doing a whole analysis for acid chlorides. So if we were trying to decide, is an acid chloride carbonyl electrophilic or not, one way we could do that is using the structural analysis tools that we've been developing over the course of this section. So we'll start by identifying the substituent that we really want to focus on. For us, it would be the chlorine, because implicitly we're going to be comparing the structure to things like esters or amides or ketones. Well, I know that a carbon-chlorine bond is fairly polarized toward the chlorine, so that means the chlorine is going to be an inductive acceptor. And that should basically make the carbonyl carbon a little bit more electrophilic than if this chlorine were, say, a carbon. We also know that the chlorine is not an alkyl substituent, so we have no hyperconjugation. And then finally, we can assess resonance effects. It looks to me like the chlorine has a lone pair. So, well, I guess the chlorine is a resonance donor, right? Draw my resonance structure for completeness sake. I notice a couple of things here, though. One is that this chlorine is a fairly electronegative element, and now it's bearing a positive charge. That's a problem. But the thing that I notice that's even more important than that is that I have a carbon-chlorine pi bond. And that should be a very long bond because chlorine is in the third row. So even though we could say that the chlorine is technically a resonance donor, it should be very poor at this role. So let's say very weak resonance donation. This will actually be worse even than in the sulfur of the thioester, because not only is this bond super long, but chlorine is more electronegative than sulfur. What I'm seeing here is mostly this inductive effect, which should be fairly significant. Chlorine is a highly electronegative element, right? I've got no donation from hyperconjugation, and let's say basically essentially none from resonance, maybe a teeny amount. And that means that this chlorine is like a net acceptor. If we actually think back to all of the examples we've seen in this video series, in the ester, in the amide, in the ketone, in the aldehyde, in the thioester, we've never seen a net acceptor before. We've only seen differences in the amount of net donation, either because of hyperconjugation donation or resonance donation. So acid chlorides are kind of unusual in that they are, or the chlorine rather, in the acid chloride, it's actively removing, in total, removing electron density from the carbonyl. And this carbonyl carbon is already pretty highly positively charged because of the oxygen. So from this analysis, we should expect acid chlorides to be very powerful electrophones. So that's our prediction. We could test this. We could take this compound and we could do the same half-life assay using water as our reference nucleophile. what we find is the half-life we can barely measure. We only can estimate it. It's way less than 1 minute. Essentially, the reaction between water and an acid chloride is it's almost instantaneous. I mean, it definitely has a half-life, but it's not something that we could easily measure. So we can see that we span a huge range in reactivity. We go from acid chlorides, which have half-lives when they react with nucleophiles of, let's say, a second or two, right? All the way to amides, which have half-lives of 4,000 years. They're still electrophilic at carbon, but their reactivity is so different just because of what these substituents do. And that's really the beauty of carbonyl chemistry, is that at one point it's extremely simple. Carbon's electrophilic, right? But how electrophilic varies dramatically. And my argument would be that this is one of the pivotal features that shows up in structural biochemistry. There's a reason why peptides and proteins and enzymes, those are all made up of polyamides. The backbones of these molecules are stitched together using amide bonds because those bonds are very stable. It's very difficult for them to come apart, even though there's water all over the place. If we did the same thing where we made molecules for biochemistry that had a bunch of acid chlorides in them, that's a problem because these compounds exist in cells that have water, and these structures react almost immediately with water. Right? So you're going to see carbonyl chemistry a lot for the rest of this semester, but you're also going to see a lot of carbonyl chemistry when you take biochemistry. And it's really the varying nature of these substituents that's going to give rise to all of the diversity of functions and properties that you'll see in a variety of different contexts as you work more with the structures of biologically relevant molecules. So in the final video for this series, we're going to turn our attention to the nucleophilicity of oxygen for carbonyls. And what we'll find is that all of the framework we've developed of looking at induction, looking at resonance, looking at hyperconjugation, we use it in the exact same way. And moreover, there's a direct correlation between the nucleophilicity of the oxygen atom of a carbonyl and the electrophilicity of that carbonyl's carbon.